Take a moment and glance at your surroundings. There's illumination all around you. The reason you can perceive everything in this space is that photons are entering your visual receptors. It sounds straightforward, doesn't it? But here's something to consider. At this very moment, electromagnetic radiation from every single object in your vicinity is propagating in all possible directions. When your gaze falls upon something, radiation from that particular object is reaching your retinas. Simultaneously, radiation from you is traveling toward that same object. Electromagnetic waves are intersecting everywhere, overlapping with one another, traversing identical regions of space. How is this even possible? How can countless billions of electromagnetic rays propagate in every conceivable direction without creating complete disorder? How do you perceive a distinct image when this apparent chaos is occurring? And we're only talking about the visible spectrum here. At this precise instant, radio transmissions are propagating through your location. Television broadcasts, thermal radiation emanating from your body, radar signals from aircraft, cosmic X-rays from deep space, all of these are traveling through identical space, through your body, simultaneously. Every single one of these is fundamentally the same phenomenon as light, just operating at different wavelengths. So let me ask you this. What is light, really? Not the simplified answer they gave you in your education. That explanation is incomplete and possibly incorrect in ways that actually matter. The genuine answer, what electromagnetic radiation actually is and how it propagates from one location to another, is so peculiar, so radically different from anything in everyday experience that when you finally grasp it, your entire perception of the world transforms. Let me show you something extraordinary. But before we dive into this mind-bending journey through the nature of reality itself, hit that subscribe button for Discover Physics. We're exploring the universe's deepest mysteries, one photon at a time. Now, let's unravel what light really is. Picture yourself sitting beside a swimming pool. Multiple people are diving into the water. Splash, splash, splash. Wave patterns spread across the water's surface, ripples intersecting with other ripples, creating what appears to be complete chaos. Now, imagine a remarkably intelligent insect positioned in one corner of that pool, just sitting there motionless, sensing the water as it bumps against its body. The wave patterns are hitting this insect from multiple directions at varying rhythms with different intensities. Could this insect, merely from detecting those wave patterns, deduce what's occurring throughout the pool? Could it determine who entered the water, where they entered, the timing of their entry, everything that's happening across the entire pool? This sounds completely impossible, doesn't it? But remarkably, in principle, all of that information exists within those waves. That's precisely what you're accomplishing right now. When your gaze falls upon something, the electromagnetic radiation arriving at your eye consists of waves, exactly like that pool, except existing in 3 dimensions rather than 2. Waves propagating in every direction, crisscrossing one another, overlapping, creating what appears to be a complete mess. And your eye, it's merely an 1/8 of an inch aperture, a minuscule detector particularly sensitive to waves arriving from specific directions, not sensitive to waves from your peripheral vision, unless you rotate your eyeball to reposition that aperture. From this apparent chaos of wave patterns, you extract an image of the world around you. You determine what you're observing from a distance, And here's what's genuinely incredible about this process. When you're looking directly at me, someone positioned to your left can simultaneously see someone standing to your right. The electromagnetic radiation is propagating in this direction. The radiation is also propagating in that direction, waves traveling in all directions simultaneously, a complete network of electromagnetic information. It's not comparable to arrows passing through one another. It's something oscillating the electric field like water height, moving up and down, some physical quantity vibrating everywhere throughout space. The combination of motions is so elaborate and complicated that the result produces an influence that enables you to see me, while remaining completely undisturbed by the fact that there are influences enabling that other person to see someone entirely different. There's this tremendous mess of wave patterns distributed throughout all of space. Electromagnetic radiation bouncing around the room, propagating from one object to another. Most objects don't possess eighth-inch apertures to detect it, so they're not actively receiving this information. But the electromagnetic radiation exists there anyway, reflecting off this surface, bouncing off that surface, all of this happening simultaneously. And yet, remarkably, we can sort it out with this little biological instrument called an eye. We exist in an invisible ocean of electromagnetic radiation. But that's merely visible light, the wave frequencies your eye can detect. Think about those pool waves again for a moment. Some waves are large, some are small. Some are slow, long swells rolling across the surface. Some are quick, short ripples darting everywhere. Your hypothetical insect might only study waves between certain size ranges. Turns out, your eye only utilizes waves between certain lengths too. Except those lengths are incredibly tiny, approximately 100,000th of an inch. What about the longer waves, though? The slower swells in our electromagnetic ocean. Those represent thermal energy. We perceive them as heat, infrared radiation. Our eyes don't register them visually, but they're absolutely there, filling the space around us. Pit vipers, snakes, that inhabit desert environments, have evolved a special organ that can detect these longer electromagnetic waves. They can pick up small mammals radiating body heat. They can see these creatures in complete darkness by detecting infrared radiation. We humans can't accomplish that. Our eyes simply aren't constructed for it. And the waves get considerably longer, much longer than that. Radio waves, identical phenomenon to light, exactly the same kind of wave propagating through space, just longer, much longer, in wavelength. Which means, right now, sitting precisely where you are, there's not only the visible light enabling you to see this page or screen. There's also information from radio broadcasting stations. Moscow radio broadcasting at this very moment. Signals from Peru, radar from an airplane calculating where it is in the sky, all of this coming through this room right now, through your body, plus X-rays from medical facilities, cosmic rays from distant celestial events, all the same kind of electromagnetic waves, exactly the same physical phenomenon, just shorter, faster vibrations of the electromagnetic field. It's all genuinely there, filling the space around you. You don't believe it? Pick up a piece of wire connected to a box, a radio receiver. The electrons in that wire get pushed back and forth by the electric field oscillating at just the right speed for certain long electromagnetic waves. Turn the tuning knobs to get the oscillating just right, matching the frequency, and you hear Moscow radio broadcasting, then you know it was there all along. How else could it have gotten there? It was there the entire time, propagating through that space. You only become aware of it when you turn on the radio receiver, all these electromagnetic phenomena propagating through the room at the same time, occupying the same space. Everybody knows this fact intellectually, but you have to stop and genuinely think about it to really experience the pleasure, the absolutely inconceivable nature of it all. For centuries, natural philosophers argued about what light genuinely is at its fundamental level. Newton declared that light is made of particles, little bullets shooting through space. Corpuscles, he called them. That's why light travels in straight lines, he reasoned. That's why you can't bend it around corners like you can with sound. Huygens disagreed completely. Light is a wave, he insisted, like sound waves, like ripples propagating in water. Waves spread out in all directions. Waves interfere with each other, creating patterns. They couldn't both be correct, could they? The argument raged for over 200 years. Then came experimental evidence that seemed to settle the question definitively. Scientists shined light through two narrow slits cut in an opaque barrier. What do you observe on a screen positioned behind them? If light were particles, you'd expect to see two bright strips, bullets going through slits and hitting the screen. But that's not what happens at all. You see a pattern of alternating bright bands and dark bands. Interference, exactly what waves do when they overlap with one another. When two wave crests meet at the same location, you get brightness, constructive interference. When a crest meets a trough, they cancel each other out, creating darkness, destructive interference. Light must be a wave. Case closed, right? Except then someone built a detector sensitive enough to catch individual photons one at a time. And what happened? Click, click, click. Individual arrivals, like bullets striking a target, like discrete particles. But wait, there's more to this story. Send photons through one at a time, individually. Surely a single particle can't interfere with itself, can it? It does. Send one photon at a time through the double-slit apparatus, and the interference pattern builds up gradually. Each individual photon seems to go through both slits simultaneously, like a wave would. So which is it, wave or particle? Here's what most people won't tell you, what most textbooks gloss over. It's neither. Light is not a wave. Light is not a particle. Light is light, its own unique phenomenon. We don't have a proper word for it because we don't have anything comparable to it in everyday experience. We attempt to describe it using familiar concepts from our macroscopic world, waves, particles, but those are just approximations, mental crutches for our imagination to grasp something fundamentally different. The reality is considerably stranger than either description. Photons are real, individual quanta of electromagnetic energy. You can count them individually. They make particle detectors click, but they don't behave like little bullets flying through space. They behave according to quantum mechanics, which means they explore all possible paths simultaneously, like waves spreading out in all directions. When you try to observe which slit a photon goes through, something remarkable happens. The interference pattern disappears. The wave behavior vanishes completely. You get particle behavior instead. Not because photons are sometimes waves and sometimes particles, switching back and forth, but because asking which slit is asking a particle question, demanding a particle-type answer. And when you ask particle questions, when you set up particle-type measurements, you get particle answers. The photon doesn't decide to be a wave or a particle. It's always itself, always a quantum object. What changes is how we choose to measure it, what questions we choose to ask nature. This isn't philosophical speculation or interpretation. This is how nature actually works, how reality actually behaves. And it's far stranger than anyone imagined before quantum mechanics was developed. So if light isn't particles flying in straight lines like Newton thought, why does it appear to go straight? Here's where things get genuinely beautiful, where the mathematics reveals something profound about nature. Light takes the path of shortest time. That's Fermat's principle, discovered way back in the 1650s. Out of all possible paths light could take to get from point A to point B, it takes the one requiring the least amount of time. Sounds simple and obvious, doesn't it? But the consequences of this simple principle are extraordinary, explaining countless phenomena we observe. Why does light travel straight in air? Because a straight line is the shortest distance between 2 points. And if light travels at constant speed through a uniform medium, shortest distance automatically means shortest time. Simple geometry. Why does light bounce off a mirror at equal angles? Angle of incidence equals angle of reflection. Because that's the path of shortest time between source, mirror, and destination. You can prove it rigorously with geometry. The quickest way to get from point A to a mirror surface and then to point B is to hit the mirror at exactly the angle where the incoming and outgoing angles are equal. Now, here's where the principle gets really interesting, where it explains something that seems mysterious. What happens when light travels from air into water? In water, light travels slower, approximately 25% slower than in air. The electromagnetic wave slows down in the denser medium. So imagine you're standing on land and someone's drowning in the water some distance away. What's the fastest way to reach them? Straight line, right? Actually, no. You run considerably faster than you swim. So tactically, you should run a bit farther on land, even though it's a longer path overall, to spend less total time swimming through the water. That's exactly what light does when entering water. It doesn't go straight when transitioning between media. It bends at the interface. It travels farther in the fast medium to spend less time in the slow medium. This bending phenomenon is called refraction. The mathematics works out perfectly, precisely. The angle of bending depends on the ratio of speeds in the two media. This relationship is Snell's law, discovered experimentally, but Fermat's principle explains why Snell's law works at a fundamental level. It's all about minimizing travel time. Once you understand that light takes the path of shortest time, all sorts of strange phenomena suddenly make sense, become predictable. Mirages on hot roads. You see what looks like water on the pavement ahead of you, but when you get there, dry as a desert. What you're actually seeing is skylight reaching your eye by following a curved path through the air. How is this possible? The air just above the hot road surface is hotter than the air at higher elevations. Hot air is less dense, thinner than cool air. Light travels faster in thin air than in dense air. So instead of coming straight down from the sky to the road surface in a straight line, the light can save time by curving through the region where it goes faster, where the hot air is. It dips down into the hot layer near the road, speeds up as it travels through that faster medium, then curves back upward to reach your eye. You see sky, but the skylight is coming from the road direction, from below. Your brain interprets that as a reflection from a smooth surface, water. It's an optical illusion created by light taking the path of least time through varying air densities. Here's another one that's even more surprising. When you see the sun setting on the horizon, appearing to just touch the edge of the Earth, it's actually already below the horizon. You're seeing a ghost of the sun's position. Earth's atmosphere is thin at the top, progressively denser at the bottom where we live. Light from the sun travels slower in dense air than in thin air. So instead of coming straight to your eye in a direct line, it curves gradually. It stays higher in the atmosphere longer, where it travels faster through thinner air, then bends downward to reach you at the surface. The sun appears to be positioned on the horizon, but it's actually already well below it, hidden behind the Earth's curvature. The atmosphere bends the light rays. We see ghosts of the sun's true position, delayed images from the past. Now, let's make something useful with this understanding, a lens. Suppose we want all the light leaving point P to arrive at point P prime. Focus it precisely. Bring it all together at one location. Light traveling straight from P to P prime. Fine, that's one possible path. But how do we make light that goes to some other point on a piece of glass also end up at P prime? How do we create focus? If light always takes the path of least time, it won't want to take all these different paths through the glass. It'll choose the fastest one, unless we make all the times equal. That's the secret of lenses. A lens makes all paths take the same amount of time. Here's how this works. Glass slows light down compared to air. So, if we take a ray that would naturally travel a longer distance to get from P to P prime, we can insert some glass along its path to slow it down, to add delay. We make up for the extra distance by adding extra time delay through the glass. The geometry works out perfectly. We end up with a piece of glass that's thicker in the middle, thinner at the edges. All paths, straight through the middle, angled through the sides, take the same time. That's a lens, fundamentally a device that equalizes travel times for light rays coming from a single source point. The same principle works for curved mirrors. Want to collect starlight from billions of miles away and bring it to a precise focus? Make a curved mirror. Shape it carefully so that light hitting anywhere on the mirror's surface takes the same total time to reach the focal point. That particular shape is a parabola, a specific mathematical curve. The famous 200-inch Palomar telescope uses exactly this principle with its enormous parabolic mirror. All optical instruments, telescopes, microscopes, eyeglasses, camera lenses, work by manipulating travel times, making some paths faster, some slower, to control precisely where light goes and how it focuses. But here's the deepest question, the one that really makes you think. How does light know which path takes the least time? Does it somehow sense the nearby alternative paths? Check them against each other. Choose the best one before traveling? How can it possibly know? The answer is yes, in a way that's going to seem strange. Light does check the nearby paths. That's a feature you absolutely can't explain with straight lines and rays, with classical particle thinking. That's where wavelength comes into the picture. The wavelength tells us approximately how far away the light must check other possible paths. It's hard to demonstrate this with visible light because the wavelengths are so incredibly short, microscopic. But with radio waves, say 3-centimeter waves, the effect becomes much larger and more obvious. Set up a source, a detector, and place a slit between them. Radio waves propagate from source to detector through the slit. Fine, that works. Make the slit narrower, Still works perfectly. Now move the detector to the side, off the direct path. The waves won't go there through a wide slit. Why not? Because they're checking several paths nearby, and those different paths correspond to different travel times. The waves from different parts of the wide slit interfere with themselves. They cancel out through destructive interference. But close the slit down to a very narrow crack, narrower than the wavelength. Now there's only one path available. The waves have nothing to compare against, no nearby alternative paths to interfere with. So they take it, even though it's not the shortest path. With a narrow slit, more radiation actually reaches the sideways detector than with a wide slit. Paradoxical, but true. You can do this experiment with visible light too. Here's how. Find a small bright light source. A distant street light or sun reflection in a car bumper works well. Hold 2 fingers in front of one eye, close together. Look through the crack between them. Squeeze your fingers together very gently, making the crack narrower. The light, which was a small dot, becomes elongated. It stretches into a line, and if you look carefully with attention, you'll see fringes, bands along the edges, colors separating out. Why is this happening? The fingers are positioned very close together. The light spreads out at an angle as it passes between them. It comes into your eye from several directions instead of one single direction. This is light not traveling in straight lines. This is light checking nearby paths. Light behaving exactly like a wave. So, what's actually happening at a fundamental level? What is light really doing? Here's the modern understanding, the quantum mechanical picture that emerged in the 20th century. Light is made of photons, real particles, real quanta of electromagnetic energy. Detectors click when individual photons arrive. The brightness of light is proportional to the number of photons arriving per second. That's the particle aspect. But photons don't travel like bullets flying through space. When a photon travels from point A to point B, it doesn't take just one path. It explores all possible paths simultaneously, every single path, no matter how crazy or indirect. For each possible path, you draw a little arrow in the complex plane, a mathematical object called a complex number. The angle of that arrow is proportional to the time that particular path takes. The faster the light oscillates, the more the angle rotates. That's frequency, the oscillation rate. Different paths take different amounts of time, so the arrows point in different directions. Now add up all the arrows, all possible paths contributing. The probability that the photon arrives at the destination is proportional to the square of the length of the total sum of all those arrows. Here's what happens near the path of least time, the classical path. The time doesn't change much as you vary the path slightly. So arrows for nearby paths all point in roughly the same direction. They add up constructively, reinforce each other, contribute significantly. Far from the path of least time, small changes in path produce large changes in time. The arrows point all over the place, in every direction. They cancel out, form a tight spiral that contributes almost nothing. Almost all the probability comes from paths near the minimum time path. That's why light follows the path of least time. Not because it only takes that path exclusively, but because all the paths far from it cancel out through quantum interference. The paths that don't minimize time destroy each other's contributions. This explains why you can block part of a mirror, and it still reflects almost normally. You're just removing some of the arrows from the spiral ends, the paths that barely contribute anyway. The central cluster of arrows near the minimum time path is what matters. That's what determines where the light goes. This is the connection between the photon picture and the principle of least time, between particles and waves, between quantum mechanics and classical optics. Light takes all paths, explores all possibilities, but only paths near the minimum time contribute significantly to the final result. Remember those pool waves of different sizes? Light comes in different wavelengths, and we give them different names based on their wavelength ranges. The longest electromagnetic waves, meters to kilometers long, are radio waves. AM radio, FM radio, television broadcasts, all electromagnetic waves, just very long ones propagating through space. Shorter waves, centimeters to millimeters, we call microwaves. Radar systems use these. Your microwave oven uses these to heat food. Shorter still, fractions of a millimeter. Infrared radiation, heat radiation, what you feel emanating from a hot stove or fireplace. Then comes visible light, the incredibly tiny range our eyes evolved to detect. About 400 to 700 nanometers. That's 4 to 7 ten-thousandths of a millimeter. Blue light is short wavelength, around 450 nanometers. Red light is long wavelength, around 650 nanometers. Shorter than blue, ultraviolet radiation. What gives you sunburn, what damages DNA, what we can't see but insects can. Shorter still, X-rays, what doctors use to see your bones, to image the inside of your body. Shortest of all, gamma rays from radioactive decay and violent cosmic events like supernovas and black hole collisions. All the same phenomenon. Electromagnetic waves, oscillating electric and magnetic fields propagating through space at the speed of light. The only difference between them is wavelength, is frequency. Different wavelengths, different properties, different interactions with matter. Radio waves pass through walls easily. Visible light doesn't. X-rays pass through flesh. Visible light doesn't. But it's fundamentally all light, all electromagnetic radiation, all the exact same thing at different frequencies, and it's all present in this room right now, filling the space around you. Radio signals from thousands of broadcasting stations, infrared radiation from everything warm, including your own body, visible light bouncing around between surfaces, ultraviolet from the sun penetrating through windows, cosmic rays from distant galaxies, particles accelerated to incredible energies, all the same kind of electromagnetic waves, all coexisting in the same space, all passing through each other without interfering destructively, a complete network of vibrating electromagnetic fields filling every point in space, overlapping, combining. So what is light at the end of all this? Not a wave traveling through a medium, not a particle flying through space. Light is light, its own unique phenomenon. We don't have a proper word for it because we don't have anything comparable to it in everyday experience with macroscopic objects. It's a quantum object, something that doesn't have a classical analog. When you're not looking, when you're not measuring, photons explore all paths, interfere with themselves like waves spreading out. When you detect them, when you make a measurement, they arrive as discrete quanta, producing clicks in a detector like particles. Both aspects are real. Both are true. There's no contradiction here, no paradox, just two aspects of the same quantum reality, revealed by different types of measurements, different questions we ask nature. We evolved to understand everyday objects, macroscopic things we can hold in our hands, throw, catch. Light is none of those familiar things. Light is something else entirely, something genuinely alien to our everyday experience. But we can understand it by following the mathematics carefully and doing experiments, and they lead somewhere strange and beautiful, somewhere unexpected. Think about what's happening right now, at this very moment. Photons from the sun, traveling 93 million miles through space. Infrared radiation from everything warm, from every living body. Radio waves from hundreds of broadcasting stations. X-rays from medical facilities. Cosmic rays from distant stars and galaxies. All passing through the same space at the same time, through your body, right now. A tremendous mess of overlapping waves, countless frequencies, countless sources. And yet we can sort it out somehow. Tune a radio receiver and hear a single station clearly. Look with your eyes and see a coherent image, not scrambled chaos. Everybody knows intellectually that electromagnetic waves fill space all around us. But you have to stop and genuinely think about it to really experience the pleasure, the absolutely inconceivable nature of nature itself. When you understand what light is, really understand it at a deep level, the world around you is far stranger than it appears on the surface. Far more beautiful, far more interconnected, and that's what physics is fundamentally about. Expanding our intuitions beyond everyday experience to grasp nature as it actually is, in all its strange quantum glory. That's the beauty of it, the terrible, wonderful beauty of understanding reality itself. If this journey through the quantum nature of light expanded your mind even a fraction, subscribe to Discover Physics and join me as we explore more of these profound mysteries. What other aspects of reality seem simple but hide incredible depth? What else that we take for granted is actually impossible, yet happens anyway? There's so much more to discover. Hit that like button if photons exploring all paths simultaneously broke your brain a little bit. Share this with someone who thinks they understand light. They probably don't. Not really. Not like this. And drop a comment below. What hit you hardest? The wave-particle duality? Light checking all possible paths? The fact that you're swimming in an ocean of invisible electromagnetic radiation right now? I'll see you in the next video, where we'll explore another place where everyday intuition completely fails and reality gets beautifully weird. Until then, keep questioning everything. That's how we understand the universe. This has been Discover Physics. Thanks for watching, and remember, the universe is far stranger than you think.